Hey there, my name is Mike, and welcome to my channel. Today we begin our discussion on kinematics. This is the first real bit of physics that we get to do together, and what a joy it is. Kinematics is the cornerstone of classical mechanics. The field has been around for a very long time, almost 400 years, and it started out with something called the Merton rule. This was something that philosophers at Oxford University discovered, and it was a very simple way to plot and understand the motion of a moving object in terms of its acceleration, its velocity, and its displacement. These are three quantities we're going to come back to time and time again in this unit. But from these three quantities, there are all sorts of useful information that you can extrapolate out. For instance, the distance an object covers while it moves at a constant speed can be found just by multiplying that velocity that it's moving at with the time elapsed during the motion. In other words, distance equals rate times time. Most of us know this equation, but in the next few videos, we're going to see how far you can actually take these concepts. And it goes much further than you might think. The kinematic equations will immediately give you the tools to model phenomena like the acceleration of a falling object, the trajectory of an arrow, or even the path of a rocket. So we're going to begin by defining a couple terms today. The first and foremost of which is this idea of displacement. And I want to prime your brain a bit because we are not going to talk about it in terms of 2D and 3D. It's very fun to describe vectors in terms of three-dimensional space. It's very fun to describe physics in three-dimensional space, quite frankly, because it looks really cool to do so. When you whip out diagrams like this and you start showing vectors in space that look like this, and you've got all these kind of crazy things happening between them and orthogonality and all this neat stuff, it's pretty to look at. Unfortunately, the math becomes kind of a nightmare. It's very messy if you're not well-versed in vector math and you know what you're doing. It's nicer to simplify. So what we are going to do is take this idea of displacement and distill it down to the most basic concept. So we're not going to do 2 dimensions today. We're not going to do 3. We're actually going to talk about displacement in terms of 1 dimension. And if you say, wait, what's 1 dimension? Well, if 2 dimensions is a flat sheet of paper, 1 dimension squeezes that into a line. So 1-dimensional space has a single dimension for the coordinates, which means the origin is 0. And if I were to choose a point on this, say point P0, that goes 1 unit right of the origin. And I say right, but right doesn't exist in this space. There's only forwards and backwards in this space. And that's it. That's all this dimensional line has to it. And I want to keep that in mind for what we go on here, because let's be clear about this. This line does have negatives. So anything this way is going to be a negative number. And anything on this side of the 0 of the origin is going to be positive, just like a regular graph. It's just in 1 dimension now instead of 2 or 3. So I said, do keep that in mind, but let's explore this a little more. And what I want to do is set that initial point, and I'm going to say, just pretend that this is like a road, and I'm going to drive another, 2 miles, we'll say. And I end up at coordinate, let's see, we go 1, 2, 3. So I end up at coordinate 3, and I'll stop my car there, and we'll say this is the final position. So I have gone from coordinate point 1 to coordinate point 3. You could do this in 3D too. Like if you did this, you would just end up with points x, y, z, and point maybe x prime, y prime, z prime, and in a minute you'll see why we don't do this, because this gets annoyingly messy to work with. So if I wanted to tell you about the net displacement, what I mean by that is this idea of a displacement vector tells me the smallest amount of distance that I can travel to go from my starting point to my final point. Or you might say that it's a vector that points from where I was to where I am, and it always takes the shortest distance to do so. So this is 1 dimension, which means that there's really only one way to get from point 1 to point 2. You have to actually just go there along the line. But if we pretend for a minute that this was 2-dimensional space, and I could go off of this line, and I could mosey on this way and come back around here, I might drive a lot more here, and the odometer in my car would go up, and the miles would click, and I'd run out of gas sooner. But the displacement vector would still point from where I was to where I am, and it wouldn't care about any of this path that I took personally. So do keep that in mind. The displacement vector, we're going to write this down, the displacement vector is a vector that we construct, and it points from where we are from where we were to where we are. That is the displacement vector. Doesn't matter what path we took to get there, we point from where we were to where we are. And it has a magnitude, just like any other vector. We have a direction here, and we have a magnitude. And the magnitude in one-dimensional space, we call this dx, right? Here's our x-axis. Our dx, our displacement vector, and that's what we like to call it, is delta x. The change in the x position, delta x, is equal to the final x value minus the initial x value. Now, hopefully that just makes sense, but in the rare event that it doesn't, this is why. Say again that I have a one-dimensional space, and we're going to pretend this is an actual highway this time, and I get off a gas station at mile marker 10, and I come over here and I drive for, let's say, an hour, and I end up at mile marker 70. Then immediately you would know, if I asked you, how far did I drive? The answer is 60 miles. And the math checks out. What we do is, we didn't drive this part, we started at the 10, so we subtract that from the total amount of driving that we did. 70 minus 10 is 60. X final minus X initial is delta X. So we're just generalizing it. And we're going to do a lot of that in this course. So make sure to get a good grasp of the idea that, like, hey, if something doesn't make sense, plug in numbers. Try and make sense of it that way, because these things are based in reality. And we want to make sure that we understand the reality of the situation that we work with. So this is the idea of displacement. It is a vector that simply points from where we were to where we are. And in one dimension, it's basically the same as length. But in two dimensions, if I took this super long path to get somewhere, it doesn't care. It's going to give me where we were to where we are. And that is displacement. Now, with displacement in mind, we can talk about something called velocity. And velocity is the logical expansion of what I just said here. So let's move back to our car on the interstate example. And I said that I drove off of the gas station at mile marker 10. And I drove for an hour until I got to mile marker 70. This is 60 miles, and we said that we can represent that as a displacement vector like this. Delta x is equal to 60 miles in the x direction, so the I hat direction, right? And if that's confusing to you, I do have a video talking about vectors and vector spaces. This is something called a standard basis vector. It is just the unit that we're using. And so in physics, this would be like 60 miles in the positive x direction, but it has this neat byproduct of being a very convenient way to describe directions. So this will get more complicated in multiple dimensions. Do take a look at that video. It will be linked in the playlist in the description below. We have 60 miles that we've traveled. Like I said, we did that in 1 hour. So the next logical question is to ask, how fast were we going? And most of you should shout 60 miles an hour, because we take 60 miles, and if it took us 1 hour to do so, then we've just gone at the speed of 60 miles per hour. We call this our average velocity, kind of. When we just deal with distances like this, there's no direction associated with this. We took a distance and we divided it by an interval of time, delta t, some change in time, from an initial time to a final time, or t final minus t initial. So some interval of time, delta t. We divided a distance by that. A distance is a vector or scalar quantity. It is a scalar quantity. A distance does not tell you direction. It's like the road. You just go forwards on the road. You go in the direction the road goes. There's no distance other than that. I mean, if you're out in the middle of a field, you might need directions. You might have to tell someone, go 60 degrees north of east. That would be a vector quantity. So with velocity in multiple dimensions, this becomes much more important. But in one dimension, like we're doing right now, it's just important to understand that velocity, we don't divide distance by time. We multiply displacement by time. Displacement, being a vector quantity, when we get into higher dimensions, will always give us a velocity that is also a vector quantity. So we write this mathematically as v, with that little vector symbol on it. V is equal to delta x divided by delta t. And this we say is velocity divided by or sorry, this is what we describe as velocity. And you can make sense of this, right? If delta x is displacement and we have standard units meters and a difference of time gives you seconds, then velocity spits out meters per second. And that's a great way to check to make sure that what we just said actually makes sense. And it does. So two quick things to note about this. We just described displacement and velocity. This is technically average velocity. And what that means is we talked about the length of time here, and we divided it by a just total interval of time. What happens in the real world, and you'll see this a lot if you have like a GPS tracking app, like Life 360 does this. Apple's Find My might, but like if it tells you someone's average speed on a road trip, if you get on the highway, your average speed will still be like 40 miles an hour for the whole trip because you spent a lot of time in the city at 20 miles an hour. So if I had this delta x and I said that I was in my car and I still drove 60 miles, but for the first 10 miles I went at like 5 miles per hour, and then at 50 miles in, or 10 miles in, I drove the last 50 at 70 miles per hour, and forgive me, I am just making numbers up here. This might still return an average velocity of 60. If it still took me an hour to do this, regardless of what my speed was, then it's still going to give me an average velocity of 60 miles per hour. So the way we can be more specific about it is to use a little bit of calculus. And this is where I'm kind of treading the waters here, to be honest. I don't really know. We have a very wide, diverse group of people that watch these videos. And so I don't know yet whether or not it's a good idea to go through the calculus of it and explain everything. But basically, what we can do is set this up in a different way. We've thought about this in one dimension. We're going to continue to think about it in one dimension. I'm going to just move this up. We're going to take this x-axis, and I'm going to put him up here so that I can put a time dimension down here. It's still it's still one dimension. We just have this parameter of time that we can play with. And if we describe distance as a function of time, we'll write everything like we did before. We have starting at 10, what do we call it, the 10 mile post, and then we have a mile post of 70 up here. Then in time for 1 hour, as long as we go from this point right here at 10 miles to this mile marker here at 70 miles within 1 hour in this direction, our average speed will be 60 miles an hour. So we could start off really, really slow like this. And then if we got really fast near the end, this would be an average speed of 60 miles an hour, even if we're going like 5 miles an hour here and like 100 miles an hour here. And so what we would want to do to get the instantaneous velocity at any point is to calculate something called a derivative. And so we can call this v instantaneous, and it's not going to be equal to a delta, a change in x, divided by a change in time. It's going to be equal to the derivative of displacement by time. And so this becomes d by dt of a function x of t, which is x of time. And that gives you your velocity. This is really useful later if you wanted to see a derivation of the kinematic equations, because it turns out that calculus makes this a million times simpler to understand. So now might be a good idea to plant the seeds in your head to learn some calculus, but if you don't worry too much about this stuff. It's not going to be super necessary as we move through our explanation of what this actually means, but it would be good to know. If you plan to like really learn physics, then learning calculus is a good prerequisite. But for now, just get the idea in your head that this is average velocity. Last thing I'll say before I let you go, and do like and subscribe if you found this interesting, is just a quick summary. The displacement vector here points from where we were to where we are, and it does not care about the path that was taken. It is a vector quantity, and down here we have velocity, which we described as taking that displacement vector and dividing it by an interval of time, giving us a vector quantity velocity. You now understand what that word salad actually means, so pat yourself on the back. Get some rest. You've done quite a bit of physics tonight, and I will see you in the next video for a worked example from the book. Hasta luego, and I'll see you in the next one.